that sounds like an interesting seminar. Unfortunately, it's at 5 a.m. where I am, so there's probably not a chance I'll make it. But recordings will be great. Okay, so yeah, so today we're going to be talking about the Hilbert Basis Theorem, and we're going to be giving a proof of this, as well as talking a little bit about the ascending chain condition as well. So along the way, we'll also define Grabner basis, and that's an ingredient actually to the proof of Hilbert Basis Theorem. So the goal, right? So we will solve the ideal membership problem, description, sorry, ideal description problem. And the way we do it will be, giving this basis called the Grabner basis, and also using this to prove that every ideal in polynomial ring of finitely many variables is finitely generated. So we're going to solve this problem by proving that every ideal of R, I guess R is, remember, polynomial ring in n variables, admits a finite basis. Right, so that will be the this is the Hilbert Basis Theorem. And I'll probably abbreviate it to be HBT, right? And show how to find such a basis. Actually, we won't quite do this in this lecture, but I will do it in subsequent lectures. How to find such a basis, right? And that will be the Grabner basis. Okay, so we need a definition to start with, and the definition is going to be using leading terms that we talked about in the previous lectures. So let I be a non-zero ideal of R, and we define LTI. Okay, so at the moment this is just a set, right? These are just going to be the leading terms of all of the non-zero elements of I, right? And then we make an ideal out of this. So the ideal, we don't have special notation for this. We're just going to write the ideal generated by LTI. Is called the ideal of leading terms. Of the leading terms. Okay. So so this will be a fundamental thing that we're going to use to prove our theorem. And you might wonder, right? So you construct this ideal leading terms, natural question, right? You might wonder this when you look at this definition. And that natural question is that, is this ideal of leading terms the same as the ideal generated by these elements, where f1 to fs is a basis, or is this true for any basis, right? Is this true? Is this true for any basis, f1, fs of I? Okay, and so you might expect the answer is not always the case, otherwise it wouldn't be very interesting. So the answer is no, this is not always the case, and I'll give you an example to demonstrate this. So the answer is no, no. And so the example is as follows. So this is not always equal, but this is always true. And that's kind of by the definition of LTI, right? So all the F1s and F1 and Fs are elements of I, so LTF1, LTFS are in LTI. So of course, the left-hand side, the ideal generated by the elements on the left-hand side of this equation, of course belongs, sorry, right-hand side, of course belongs to the left, but the reverse containment is not always true. And so the example, counterexample, I guess, to this equality is as follows. So let I be the ideal generated by two elements, and I guess the ambient polynomial ring will be obvious once I list what F1 and F2 are, where F1 is x cubed minus 2xy. I always have to be careful now when I write down these polynomials to make sure I copy the right thing down. Otherwise, somebody's going to tell me I made a mistake. Plus x. Okay, so right, so we're inside polynomial ring in, I guess there are only two variables, right? Two variables, and I guess the base field is, let's just take it to be complex numbers. Okay, so I'm going to go over there to the third board. Right, so we're going to use the graded lexicographical order. Right, then LT of F1 is equal to x cubed, and LT of F2 is equal to x squared y. And so, so what this means is that the ideal generated by these two, LT F1, LT F2, that's equal to x squared x y. Right, so I guess, don't know if we wrote ideals like this previously, but this just means that you have an ideal generated by x cubed and x squared y. You can like factorize the x squared out of everything in this ideal, so we just stick that at the front. So this is, you know, the ideal generated by these two elements is the same as the ideal generated by x and y, and you just multiply everything in sight by x squared. Okay, so that's the ideal generated by these two elements, but we're gonna write xf1 minus xf2 minus yf1, xf2 minus yf1, and that's equal to minus 2xy squared plus x squared minus 2xy squared, and you're going to get x squared remaining. And because we're using kind of R linear combinations of F1 and F2 putting together, you're going to get an element of I, right? You're still in the ideal generated by F1 and F2. And so, so LT of this element is the same, right? X squared, there's only one thing there. So LT of this element, right, is itself, and that's inside LTI, right? Remember the definition of LTI was that you take all the elements in I, and you only look at the leading terms, and we found an element in I which is the same as its leading term, so this guy's in I and LTI, but right, this x squared is not in the ideal that we wrote down here, right? So this thing here, in particular, does not contain x squared, because if it did, well, then it wouldn't be this ideal, right? So, but I said but too many times. So right, so x squared in there, and x squared is not in LT F1, LT F2, right? So this is a counterexample that shows that so LTI is bigger, right? Bigger than LT F1 and LT F2, right? So equality is not always true for LTI and LT of any old basis. And so right, so when, sorry, shouldn't move to that, move to the right. So whenever you see something like this, right, you write down some equality that you think might be true, it doesn't always true, then you ask the next natural question is to say, well, for which basis does this hold, right? Are there any basis of I where equality holds for this equation that we wrote down on board number 2. And so the next question, right, now that we've failed the obvious guess, the next obvious question is that, does there exist a basis G1? I'll change notation a little bit because I guess it's G for Grabner basis. I'm kind of giving the punchline away, of I such that LT I is equal to LT G1 all the way up to LT GS. And I'm going to call this equation star. I'm going to refer back to it later on. So it turns out, yes, there is such a basis, and this is going to be the Grabner basis that we're going to be constructing later on. So the answer is yes. Yes. And it's a rather special class of bases, right? It has this property, and it does all kinds of stuff for us. And so to prove this, we'll need a proposition, and then we'll head into Hilbert Basis Theorem. So the proposition is that two statements, right? This LT of I is a monomial ideal. And 2, there exists, right? 2 is that there exists a basis G. Yeah. 2 is the answer to the question yes. I guess I'll just write it again. So there exists a basis G1 GS of I such that star holds. Okay, so I guess slightly out of space, so let's move over to the next set of boards. You guys are awfully quiet. Can I actually hear anybody? You guys can hear me, right?
Hello.
Yeah, you haven't made any mistakes yet.
Loud and clear.
Thanks, Ben. Okay, so the proof, I guess, the proof of 1 is pretty simple, but I'll write it down, right? Because it's almost by definition. So LTI is generated by these LTGs, right? So since LTI is generated by these LTG, right, where G is in I, this is just the definition we wrote down earlier. These are all monomials up to a scalar multiple, right? They're just, right? And, LTI is really just some scalar multiple, leading coefficient of G times the leading monomial of G, right? So, this is a scalar, I guess. Scalar is an element of K. This is, I should just write this. This is in K, and this is a monomial. And so so what one follows, right? If you can replace LTG with LMG, right? Actually, these are like non-zero scalars. Put a little cross here, right? So you can replace LTG with LMG, generates the same ideal, right? So yeah, so LTI is generated by LMG for G in I, right? And so the definition of a monomial ideal is that it's generated by a bunch of monomials, so that's it. Okay, so that's one. So now we know that LTI is a monomial ideal, and so now we can use Dixon's lemma, or lemma theorem, Dixon's lemma from last week to give us claim number 2. So this uses Dixon's lemma. Okay, and so any ideal generated by monomials, in this case, LT of I is generated by Lm of G, where G is an element of I. You can find a finite subset of these generators which also generates the same ideal, right? That's Dixon's lemma. And so, so using Dixon's lemma, any ideal generated by monomials, I guess, right, can be generated by a finite subset. What should I say? Monomials. Maybe I'll say S. Is S a good thing to use? Yeah. Can be generated by a finite subset of S, right? And so, yeah, and so, i.e., LT I is, can be generated by admits a basis. I'll just write that, a basis. And since the monomials which generate LT of I are all the form LT of G, right? We can just write them down, enumerate these. LT of G1, LT of, I guess, GS. And S doesn't have a special meaning here. I know we've used S as, the default number of generators for a generating set for an ideal, but I'm not claiming there's any special number of generators, just that it's finite. So S is just some finite number that's not related to anything. Right, so admits a finite basis, right? LTG1 to LTGS. So star follows. Since LTGI is a scalar multiple of LMGI. I don't know why I have this here. Maybe I don't even need to say this. But let me just check the statement. What did I say? Yeah, I mean.
Yeah, I don't know what the point is of talking about LM and LT as well.
Sorry, what was that?
Yeah, I don't really know what the point is of this line up that earlier where you're like LTI is LCG, LMG, I mean LTG. The second line, that should be an LT of G, not LT of I, right?
Oh, yeah.
But then I don't really know what this observation is for. I mean,
I don't know. I think strictly speaking, monomials don't have coefficients in front of them, but we all know that it doesn't matter.
Right. Oh, okay. Mm-hmm.
Yeah.
Yeah, I think it's just saying that, like, okay, so the leading terms are not strictly monomials, but we know that up to units, they generate the same ideal anyway, so it's just sort of explicitly saying that.
Mm-hmm. Yeah, okay, fair enough.
Yeah. So really, we can do without all the LMs and just use, but like monomials are defined without coefficients, I think. So, yeah.
Fair enough.
Yeah, so when you say monomial ideal, right, those generators don't have like 2s and 3s in front of them. So maybe that, to be pedantic, I think the book was trying just to be pedantic in that case.
Don't give
I
up,
think that we
Eleanor.
need to be in a field to be able to get rid of it. Like if we're not field,
Unable to hear anybody is.
Valentine, I think you're a bit muffled, your microphone.
Hang on, let me turn up my sound. Maybe I can't hear. I was having trouble hearing Dan as well,
the
actually.
microphone on my phone, so I'm not sure where the microphone is actually, I guess. Can people hear me?
Yeah, I can hear
It sounds
you.
like
fine.
We can hear
you might
but
be
it's
covering the
really
microphone
bad
with
cell phone
something.
reception.
Oh, maybe.
Yeah, we didn't have any trouble hearing you previous weeks. I think you might be covering your microphone with something. I don't know.
But I wasn't on my
Was there a question that I neglected to understand?
I haven't heard a question.
Okay.
I think you can keep going, Ken.
All right, cool. So in that case, if you have a question, maybe you can write it in the chat, and somebody can can attend to it. Okay, so so the punchline of today's lecture is that star holds when we remove the LT, right? So the LT is in front of everything. So we've only made a statement about the leading term or the ideal leading term. So I don't care about that. We care about I, right? Because we care about the ideal I, which may not be a monomial ideal. So we use Dixon's lemma. We've made some.
Sorry, Ken. The star. That's back on the few boards ago, but I missed this. Oh, there it is. Okay, yeah. So that's just LTI is the ideal generated by LT of the generating set, right?
Yep, that's right. Yep.
Cool.
Yep. And so, right, so we're going to get rid of the LT just by removing it. And so we get a new equation, right? This is also true. So we want to say that now G1 and GS are what we found earlier. So now that this has some special meaning, I'm going to call this hash, right? So the punchline is that this also holds, right? Right, so that's true. And so we've solved the ideal description problem, right? By finding a basis for I, right? It doesn't. This is what we're going to prove. Will prove. So this is will prove. Right, so we haven't proved it yet, and that's actually in the statement of Hilbert Basis Theorem here. So here's Hilbert's Basis Theorem. So it's actually going to be in the proof of Hilbert's Basis Theorem. So for any ideal, I'm going to say non-zero ideal, right? Of I of R. There exists a basis G1 GS, right? And so the G1 GS, right, is going to be constructed like we did with the monomial ideal. So in this case the notation is suggestive. So as the notation suggests, we're going to use the basis G1 and GS from the previous proposition, right? The one that came from finding generating set for LTI, or the ideal generated by LTI, right? So so from previous proposition, right, we found G1, GS. We don't know whether the space is for I yet, so we just found some elements, GI to the GS, such that LT of I is equal to LT of G1 LT of GS. So we're going to use this this set that we found earlier, this finite set we found earlier. We're going to prove that in fact G1 to GS actually will generate I, provided that this equation of leading term ideals is true. Okay, so so then clearly, right, the first thing we need to say is that clearly G1 to GS is in, they're all in I, right? They're fished from I, right? Obviously, they're going to be in there. So we need to prove the reverse inequality. So we need to prove the reverse inequality. So conversely, oh, maybe I should say what, right? So I guess I'm going to say this is in there. Yeah. So conversely, on the next board, we move over a bit. Yeah. So conversely, so the converse is we have to prove the reverse containment. So let F be an element of I. I'm going to show that it's in the ideal generated by G1 and GS. Now, we don't know whether this is the case, but we have the division algorithm, so we're going to use the division algorithm to divide F by G1 to GS, and hopefully we can kill the remainder, and then we're done, right? So that's what we're going to do, right, when we do this, right? And use the division algorithm to write F to get. So remember, we're not using the algorithm, we're just using the conclusion of the division algorithm. So we know that we can carry out a bunch of steps to get something like this, plus ASGS plus some remainder term, right? Where some conditions on these R, right? So where no term of R, right? This is in the theorem of the division algorithm, where no term or summand of R is divisible by any of LTGI, where I ranges from 1 to S. Okay, and so, right, so now the next bit is we're just going to rewrite this very simply with R as the equation, subject to the equation, minus G1 minus GASGS. And so, right, we want to write this so that this is now an element of I, right? Why is it an element of I? Well, F is in I, and all the G's are in I, and we're just taking R linear combinations of these things, so you stay in I, right? So this is in I. And then we're going to say, well, if we want to show that R is 0, right? Because if it's 0, we're done, right? Then F, then any element of F is generated or can be written as a R linear combination of G1 to GS. So yeah, these guys are in R, right? Okay, so if R is 0, not 0, we're going to get a contradiction. Then we have this equation, R is equal to this thing, right? And so R is in I, right? So if it's not 0, then we can do LT of R, right? And LT of R is in LT of I. Well, because R is in I, then LT of I is it's just by definition is in there. And so this is actually equal to LT. This is the magic. This is what makes it all work, right? So this equation here is this, the special property of GI to GS is that the leading terms of G1 to GS generates the ideal of leading terms of I, and the leading term of R is in this ideal. Okay, and so And so in particular, LT of I is a monomial ideal. So to say that something is in the monomial ideal is the same as saying that LT of R is divisible by LT1, LT2, or LT of R, or of S, one of them. And this is a contradiction, right? So i.e. by LT of R, I shouldn't revert back to normal R. That's going to be, I'm going to keep writing my fancy R's. Is divisible by some LT GI. And I believe this was either something that Dan proved or it was in the exercises. But this is a property of monomial ideals. When you say some monomial is in a monomial ideal, it's really checkable by division by each of the elements, generators. And so this is actually a lemma 2 of section 4. So this is cool.
Hey,
Lemma.
Ken.
Yep.
Before we said that in general, you only have a subset relation between LTI and the ideal generated by all the LTGIs.
Yeah.
What I kind of forget what the condition is that makes this an equality.
Let me go back. So it was Dixon's lemma. Wait, hang on. What was your question again? You want to ask about LTGI? Can you point to the board where I should go to?
The thing that you've underlined in red.
Yep. Yeah.
What makes that an equality?
Oh, what makes that inequality? Because in the previous lemma, we constructed this is by construction, right? We found a basis for LTI and we called it LTG1 to LTGS, and we're just using this basis for LTI. Maybe more correctly, I should have written something like this, right? Yeah.
Oh, okay. But I'm just trying to think back to the situation of the first set of boards. What was the difference there?
Well, that was saying that for some sets of generators that will be true, and for other sets it will be false. We have no particular reason at that point to believe it's ever true, except we know that from Dixon's lemma it's easy to arrange for that in the case of monomial ideals. So if I give you an infinite set of generators G1, G2, ... for an ideal, and they're all monomials, Dixon's lemma says that you can just take finitely many of them and they will generate. And in particular, if those generators are leading terms of something, which is the case we have in this board set here, right? We're given some set of generators G1, G2, ... not monomials. If we take their leading terms, those generate an ideal, a monomial ideal, and we know it's finitely generated. So just take finitely many of the GIs, G1 through GS, whose leading terms generate that monomial ideal. And that's the setup we're in right now.
Okay, cool, thanks.
Yeah, so we're trying to bootstrap this from Dixon's lemma, and finding this G1 to GS is, I guess we haven't found. We didn't actually do it. We just said, well, by Dixon's lemma it exists, right? You can probably go for the proof and find this. Actually, I don't remember then. Was the proof constructive to find the GIs to GS? No, it wasn't, right? That's why we have to do this Bookburger stuff to actually find this basis. So we're not at the point where we're saying this is how we find it, right? We're just saying it's finite, and it exists, and we have it, and we're going to use this to. We don't even have to do much work to construct a basis for I. Like, we're using the same GI's work. We don't have to do fancy stuff, which is great. We're almost done, right? So by lemma 2 of section 4, to check that LT of R is inside D, was just division, and we already said that the division algorithm kind of says this is impossible, right? So there's some contradiction there, and so we're done, right? So this is a contradiction. So this is a contradiction by what I wrote in blue up above, hence R is 0. R is 0, so F is in G1 and GS, and I'll just stop it there. Like, this proves the reverse inequality, so I is the ideal generated by G1 to GS. Okay, so I'll stop here again for some questions. I guess this is a fundamental theorem in commutative algebra, right? Hilbert Basis Theorem is kind of famous. One of the things that you always learn in a commutative algebra class. But this is a cool proof. It's I mean, it's not constructive, but it's kind of, I think it's kind of easy to understand, and it uses, very elementary things, Dixon's lemma and division algorithm, for instance.
It feels like it somehow cannot possibly be this easy.
Yeah, right. Yeah.
Well, the normal proof
So-
actually seems scarier than this. Using Dixon's
Yeah.
lemma, it seems kind of pretty cheap. So if you think back to Dixon's lemma, there's I suppose one or two places there where it seems like you have to think a bit hard. Maybe that's the feeling you should associate with the Hilbert Basis Theorem. So that's kind of...
Yeah, it's really quite surprising that you can generalize it this easily.
Yeah, I remember learning Hilbert's Basis Theorem or the proof for the first time, and it was abstract, right? And this is just like, this is not super abstract. I mean, it kind of is, but you're just essentially working with ideals and elements, right? You don't have ascending chain conditions. We'll talk about that later on, but yeah.
Does this strategy generalize to the case where it's any Noetherian ring instead of just a field, or is that a lot harder?
So the Noetherian condition basically says this works. I mean, it's easy to get from the ascending chain condition to proving finite generation. So this is really the proof that a polynomial ring is Noetherian.
Right, it's just that we assumed that it's a field, but of course this is stronger than
I see what
necessary.
you mean. Yeah, I don't think this approach does much for you at all if K is not a field. So that's probably how the other proof is more general than this, which is probably why this proof is not. This is not the standard proof, I would say. I mean, most introductory courses, say in algebraic geometry, wouldn't give this proof of the Hilbert Basis Theorem. They'd give the other one. So I think that's probably the reason that this is kind of special to fields, because you only have the machinery of leading terms and so on if you work over a field.
Cool. So this basis that we found is also what we call a Grobner basis. So I'm going to apologize for not pronouncing Grobner properly, but I guess I don't know German, so that's okay. So a basis G1 of GS of I satisfying, this I is ugly, of I satisfying.
Move your ass over to the right spot, Kenneth.
Oh, sorry. Oh man, are there only 3 boards? No, I just can't count. God. All right. Thanks, Dan. So basis G1 GS of I satisfying star. So star is the LTI equals LTG1, so forth. Is called Grobner basis. Okay. And so there's an alternative characterization for this in terms of divisibility of leading terms by leading terms of G1 and GS. I guess that's probably in the exercises, although I'm not sure. But it's in the book, right? If you want to take a look at it, you can. So the corollary is that every non-zero ideal, I guess this is obvious now, zero ideal I of R admits a Grobner basis. Okay, so I'm going to give some examples, or maybe just one example. The second example is a little bit long, and I do want to say some things about the ascending chain condition. So I'll give this example, which is a carryover from the previous example. And so, or maybe it's not. Maybe it is. I'll write it again. F1 is equal to X. You guys can tell me whether this is exactly the same or not. x squared y minus 2y squared plus x. So this is not a Grabner basis, not a Grabner basis of, I guess, I equals f1, f2. Why is that? Since, I guess it's the same reason, right? Since LT of I, since x squared is an LT of I, but x squared is not. So yeah, this is just the same as the previous example. So I'm not repeating any of the calculations. I'm just rehashing the statements, right? LT of I, but x squared is not in LT. So yeah, we have an example of a non-example of an example which is a basis but not a Grabner basis. And okay, so I'll just say a few words about historical notes, and then I'll talk about the ascending chain condition. I feel like this discussion is not complete without at least some mention of the ascending chain condition, is because we usually prove Hilbert Basis Theorem using ACC, so I'll say some stuff about that. But the historical notes from the book says that Buchberger uses Buchberger was Grabner's student, and he actually invented the Grabner basis in 1965, and he named it after his advisor. And Hironaka of resolution of singularities fame also invented something called a standard basis for a power series ring in 1964, and that's a related concept, not exactly the same. I actually don't know how they're related. Maybe Dan, you know a bit more about this and can say some things.
Ken, I do have to say your pronunciation of Buchberger is even worse than Grabner.
Leave us alone, Eleanor.
Oh, well, Dan's got a lecture on what is Buchberger? So you can have them.
It doesn't exist in English. You can't do it. I'm sorry.
I'm sorry. I only have to say this once. That's it. You have to say it many times.
The B algorithm, Kenneth will say.
The B algorithm. Oh man. All right. So let's go
It's
over to
CH. It's Buchberger, but I have a Swiss accent, so I can't say it right.
All right. Buchberger. All right.
To answer your question, Ken, no, I don't have anything intelligent to say about standard bases.
Cool. I guess Google will tell us something if we Google it. Okay, so applications of Hilbert Basis Theorem, and I'll talk about ascending chain condition for ideals in R. So ACC, ascending chain condition for ideals in R. Okay. So so this is the original approach to proving the Hilbert Basis Theorem. I think this is what Hilbert actually did, and so the approach is that we show the ideals in R satisfy the ACC property, then using that deduce finite generation from the ascending chain condition, not property, condition. And so we've done things backwards, right? We've proved that the ideals in R are finitely generated. So we're gonna use this fact to prove that the ideals in R, or the lattice of ideals in R, also satisfy ACC. So have to give some definitions for what any of these things are. So one, and so an ascending chain of ideals in R is basically what it says, right? You just have an ascending chain of ideals, or in R. Two, if every ascending chain of ideals stabilizes, and I guess I don't know why I've written it like this. I guess I should define what stabilizes means, right? Let me, so I'll write it like this. So ascending chain stabilizes if there exists some integer n, big N, such that I(n) equals I(n plus 1) equals I(n plus 2), so on, right? So is the chain is the same after a finite number of steps, then everything's the same. And so then if this happens, we say that the ascending chain stabilizes. And of course, if every ascending chain of ideals in R stabilizes, then we say that R satisfies ACC. So if every ascending chain stabilizes, well, chain of ideals in R, not any other ascending chain of ideals in R stabilizes, then we say that R satisfies ACC, or the ascending chain condition. Yeah, so this definition of ascending chains, stabilization, and ACC is, well, we're saying it as a property of R, but you can easily imagine this to be a property of any old ring, right? We didn't use anything about polynomials here. We're just talking about ideals and, equality of ideals, and that's it. So this is a pretty general kind of definition, and so this is kind of why. Yeah.
Ken,
Yep.
if the chain ends at R, isn't this true? Doesn't every ascending chain stabilize at R? Am I misunderstanding the definition?
I mean, you've got a finite number of.
Right. Okay. So you have a sequence. Your chain is like a sequence, right?
Yeah.
Like a
Yeah,
finite.
I think the way Kenneth
Yeah.
wrote it is a bit misleading. What he means by the chain is this part, and this is like
Yeah.
these are all ideals in R. So, but he already
Is it
he already
supposed
said that
to be
above.
finite?
So let's just get rid of that if you don't mind, Ken.
Okay.
All right. Sounds good.
Okay. Is it supposed to be? It's not necessarily finite. Is it supposed to be countable, or does it not really matter?
It's meant to be countable, yeah.
Right.
It
Okay,
doesn't matter, of course, because if you had an
Yeah,
uncountable
yeah.
chain, you could find a countable one inside it and apply ACC to it. Yeah.
Okay. Thanks.
Cool. And so I guess the theorem is that R satisfies ACC here. So the theorem is that R satisfies.
R being a polynomial ring over a field. Yeah.
Oh yeah. Not any old ring. ACC. Okay, so the proof, right, is a proof is actually not too difficult. So you let I1, I2 be an ascending chain. So how are we going to do this? We're going to use finite generation, right? So we're going to take the union of everything we're going to take a union of all of these. We're going to construct this guy, which is, just a union of all of these pieces. Maybe IJ, but II, that's fine. So this is an ideal. Okay, why is this an ideal? Well, if you want to check, essentially it's because if you want to take two elements in here and check the conditions that define what it means for I to be an ideal, you can just go up to a finite step that contains these two elements. You can always do that because these conditions are defined on a finite number of things, and then then you're in an ideal, so everything automatically holds, right? And so that's basically it. So to check that it's an ideal, right? So then it's indeed let F and G in I, right? So then and find, well, what do I say? And there exists some m such that f and g is in IM, right? You just go out far enough to capture these guys, right? Then IM is an ideal. So f plus g in IM, that's in I, right? So you can do this with any two elements in I, so it's closed under addition, and then, you know, for any R in R, you can do the same thing, right? R F is in IM because it's an ideal, so that's also in I, so we're done, right? So, right, so this is the easy bit. So now we can use the fact that I is finitely generated, right? I is an ideal. Any ideal in R is finitely generated. So this is where the power of the Hilbert Basis Theorem is going to come in and just do all the hard work for us. Now, Hilbert Basis Theorem implies that I admits a finite basis, and we're going to call it G again, I guess. Do I want to use G? Yeah, G1, GS, right? So we have a finite basis. And again, right, we use the same trick. We have S elements. We can always go out to some big M prime, right, which contains all of these G1s and GSs, and then we're done. Anything else after that is going to be the same because we've already got all the generators of I, and that's it. And so, since there's finitely many of these, there exists some M prime such that G1 GS is in I M prime, right? And so hence I M prime is equal to I M prime plus 1 equals I M prime plus 2, and so on, because all of these are contained in I. I M is actually already equal to I, right? Right, this is actually equal to I, this is equal to I, this is equal to I, and that's it. So yeah, that's essentially how you show from finite generation that ideals in R satisfy this ascending chain condition. Now, of course, yeah, this is how, usually it goes the other way, but we've done it backwards. Okay, so yeah, any questions? Yeah, it's pretty cool. This is a much more elementary way of doing this rings and ideal stuff. I think it's quite nice. So the last thing. Oh, did you say some stuff? Sorry, I missed.
In the chat, I said that Phil when no Zorn's llama.
Yeah. Llama. Cool.
Yeah, this is
Yeah.
this ascending chain condition. I mean, this is one of Noether's great ideas. It's how we think about dimension in algebraic geometry, right? Like these kinds of chains, and the fact that these chains are always finite is how we think about affine varieties being finite dimensional, what that means. Keep in mind that dimension is not an obvious concept if you're dealing with singular varieties, because you can't just say, I mean, there are many ways of talking about dimension, but one of them is to say, for example, that a curve is one-dimensional because everywhere on it, when you zoom in, looks like a line. And similarly for a surface and a three-manifold. And that is the definition suitably unpacked for manifolds. But for singular objects, like we study in algebraic geometry, that definition won't fly because, if you just draw, I'm writing on the board now, if you draw a curve like this.
It's like a curve almost everywhere.
It's like a curve, a one-dimensional, well-behaved thing almost everywhere, but what is the dimension at this singular point here? I mean, it doesn't look like a straight line. It's clearly not two-dimensional. It's sort of one-dimensional still, but in a way that isn't that naive definition. But using this idea of dimension as being about chains of ideals, which corresponds to chains of subvarieties, if you think about it, you can still understand this as one-dimensional in a suitable sense. So the dimension would be the longest chain of affine varieties sitting inside your variety. Yeah, the smallest m where it stabilizes, up to plus or minus 1, depending how you index the start. Yeah, that's right. So we won't get time to really talk about dimension theory in this course. That's Mag 2 maybe. But this is a deep idea, to think about dimension as being about how many smaller things can you fit inside your thing, which are essentially different. What's the longest such chain you can produce? So I thought I'd just highlight that at this point.
Cool. Thanks, Dan. Yeah, that's an important concept, Mag 2. Cool. So the last thing I want to talk about is to bring this back to varieties, because this is a geometry course after all, and we haven't done anything with varieties today yet. We just talked about rings and generation and so forth. So this is one of the kind of fundamental facts about varieties, is that if you write down varieties as solutions of polynomial equations, can you find a finite number of them that cut out this variety, right? So I guess you already know the answer from Hilbert Basis Theorem. The answer is yes, right? You can just take that basis that we found in using this leading term and Dixon lemma and all that. We can actually find a finite number of equations that cut out the variety. So that's the last point of what I'm going to do today. So variety, so every variety is cut out by finitely many polynomial equations.
I guess strictly speaking, that's a tautology, the way we defined it, right? We defined affine varieties to be cut out by finitely many. So maybe you want to say something.
Didn't we define VI? I'm about to write it down, but I thought we wrote this down at some point, right? Like, okay, I actually have it in my notes, right? So far, this is, as Dan said, this requires a bit of explanation. So far, we've
Billy's happy with tautologies because he's a logician.
Yeah.
It's all
VF1 and FS. So this is a tautology because we've only defined varieties in terms of finitely many polynomials or Fs or elements of the polynomial ring. So what does this mean? For only a finite number of polynomials. But in algebraic geometry, we usually don't start there. We start with, we can also consider VI, right? This is the variety associated to not just a finite number of elements, but the entire ideal I, and this is going to be Xn, Kn, and I probably wasn't going to use Kn. I was going to use affine space. Right, and yeah, f of x equals 0 for all f in I, right? So you take the ideal and you look at all the points where all elements of the ideal evaluate to 0 on these points. And so this is not obviously generated, this is not obviously cut out by finitely many polynomial equations. And so when I talk about variety here, I'm talking about this variety, this definition, this more general definition of variety, right? So this might involve finitely many equations, but then we're going to write this down and quickly kill this notion because we already know we have Hilbert Basis Theorem. And so yeah, Hilbert Basis Theorem tells us that this is actually much simpler than it looks, right? So the proposition, I'm going to put this on the next board because, yeah. When defining VI, we call it variety, not just a set. Then before we prove that it's cheating. Yeah, I guess that's true, right?
Even better is Billy's combative animation. He's spoiling for a fight.
I guess the point, right, is that And it turns out we actually didn't cheat by defining varieties to have finitely many polynomials in them. This is the punchline, right? That we're allowed, we were justified in doing that, it turns out.
Yeah, can I put variety in inverted, like in quotes? Then we don't.
Yeah, I think that's fine.
Then you can't say anything to me now. I've put stuff in quotes. I'm safe.
I don't know
So-
why my character is punching, but I'll just leave it that way.
I remember we were able to. How do we do this?
Some words trigger various animations. I don't know
Yeah,
what it was in what you said, but
Yeah, maybe the lecturer shouldn't be punching.
that's cheating, probably.
Oh, right, yeah. Okay, so the proposition is that this vi that we defined suggestively with the letter v is an affine variety. Yeah,
I
this
think
is
this is the vibe of what I was saying.
Yeah, the AI picked up that you were saying something that,
Yeah.
that suited this animation.
Yeah, so this is a little bit tautological, unfortunately. It's a basis for I, then vi is equal to vf1 fs, right? So yeah, so I guess I shouldn't call vi a variety because the statement of the proposition is that vi is an affine variety, so it's confusing to say so. But the notation vi, whatever I define using the set notation, is in fact an affine variety. What this means is that you can use a finite number of generators of the ideal to give you the same variety. So so the proof, right, is that we use Hilbert Basis Theorem. So by Hilbert Basis Theorem, there exists a basis f1 to fs. I'm hearing some static coming through my speakers. Is that me or is that somebody's microphone going crazy? Oh, well, that's okay. It's not super crazy, but
I think it could
all
be
right, there you go.
I can see
Thanks.
the microphone indicator move.
So, claim. The claim is that what we wrote down there, or maybe I shouldn't do I'll just write this as, what symbol should I use? I'll use an asterisk. Haven't used that yet. Claim is true. Right. I guess, yeah, with this basis, right, f1 to fs, right? So I'll just say that this is clear. Why is it clear? Because f1 to fs, they're all elements of I. Then if points vanish on f1 to fs, they must vanish. Oh, no, sorry, other way around. If a point is evaluated to be 0 by all elements of I, obviously it's going to be true for f1 to fs, since f1 to fs is they're elements of I, right? So it's by definition. So that's clear. So the other containment, let x in v f1 to fs, right? So a point which is only 0 for this finite number of things, and then we just write out what the thing is, right? So then, since any f in I can be written as R linear combination of f1 to fs, can be written as f equals a1 f1 plus, I'm going to leave some space, sfs, right? I'm going to erase this f so I have more space. I'm going to evaluate these polynomials for once, so I need some space to evaluate them. And so if we do this, right, so if x is a point such that is 0 for where f1 and fs are all 0, then this equation tells us that f is also 0 at x, because you can write f as some linear combination of these f1s, the fs's, and they're all 0. So it doesn't matter what a1x or asx are. They're all going to be just some number times 0. And so maybe I'll go to the back. I guess it's not far to walk to finish off this proof. Not the best break because the equation that I need is on the other side of the board. But yeah, if x is in Vf1 to Fs, then what this means is that F1x is equal to 0. Well, F1x all the way up to Fsx is equal to 0, hence therefore f of x is equal to a1x f1x. I guess it's not too hard to write out. Equals a1x0 plus asx0 equals 0 because 0 kills everything, right? So what this means is that x is in Vi, right? F is some random, not arbitrary element of I. So we're showing that fx is 0, so that's it. So that basis that we found, that is supposed to exist by Hilbert Basis Theorem. We haven't found it. We just claim that such a thing exists. It's going to help us cut out the variety as well, right? So you only need a finite number of equations for any of these VIs, right, that you want to define in terms of an entire ideal. So so we were justified in defining affine varieties as V of F1s to Fs's because even if we generalize this a little bit to ideals, we end up getting the same objects, which are just V of some finite number of polynomials. Okay, so I think that's it for today. I'm surprised I finished a little bit earlier, especially given that I lost 10 minutes. Any questions?
I'll make a comment while people are thinking about questions. Yeah, you touched on it there at the end. It's very interesting to note that, okay, so we're given some ideal and we compute, well, we don't compute, we write down V of I, but it remains very unclear, given that definition, how to check effectively if any point is in that affine variety. We know from the theorem it is an affine variety, but if I give you a point, how would you check that it's in that affine variety? In principle, you'd have to check a condition, fx equals 0, for infinitely many f's.
Yeah.
So then the problem of finding a finite generating set for the ideal is not some just sort of technical algebraic thing. It becomes a very clear conceptual problem, right? How do you find an effective means of determining if any point is actually in the set? Well, you need to find a generating set. That's what a generating set is. It's a finite list of checks that you can do. And then it's not... so how do you actually run that proof to find a finite generating set? Well, you'd have to find, given the proof we gave of the Hilbert Basis Theorem, you'd have to find some set of elements whose leading terms generate the leading term ideal. And that's what the Buchberger algorithm is. It's going to find for us such generating sets. They're called Grosvenor bases. So that's kind of the trajectory of this course in a way, right? So we started with affine varieties, and now we're learning how to actually figure out the finite list of conditions to check to determine if a point is in a general variety or not, which is defined perhaps by infinitely many equations. And this does come up very naturally. So it's quite natural actually that you'll end up with an ideal where you don't ahead of time know a finite generating set. For example, you might intersect some complicated collection of things and not know ahead of time a finite generating set. And among finite generating sets, there are better ones that are more effective than others, and so on. So this is what the discipline of computational algebraic geometry is about.
Yeah, I mean, this kind of thing happens in math, right? You often see definitions where you look at a condition and you think, how am I ever going to check this? There's like infinitely many things here, right? And then I think in this case, it's really nice that you can boil it down to a finite number of checks, and then you can say when a point is in a variety, right? So yeah, so this is super cool.
Yeah, any questions for Ken?
So we discussed a while ago this idea of like what happens when you go from the variety to the ideal and back, right? And I guess the point is that if you have a Grobner basis, then it's equal, right? And in particular, you can always find a Grobner basis.
Equal. I mean, it depends, right? Like that going back.
I mean, if I take my variety that's generated by a Grobner basis, and then I take its ideal, and then I take its variety, I get the same thing, right?
No.
I don't.
So if you take
That's not the point.
No? Okay.
yeah, so if you take x cubed, for example, in the polynomial ring with one variable x cubed is a Grobner basis for that ideal. But if you take the vanishing set, inside, maybe I should write, so
Right.
I'll write on the second board here. So if you take I is generated by x cubed and take this inside the polynomial ring with two variables, x and y. If you take the vanishing set, well, x cubed vanishes exactly where x vanishes, right? Namely on the y-axis. So if I take I to be that and I prime to be just the ideal generated by x,
Yeah.
they'll have the same vanishing sets. And when you take I of v, this common v, I'll call it v. So when you take then I of v, you get back I prime, not I.
Yeah, so I guess the point is that Grobner bases are ways to express ideals, but the fact that this operation of going from an ideal to a variety back to ideal still kills nilpotence, that's got nothing to do with the Grobner basis, right?
Yeah, so I guess we won't really cover it in this course, but geometrically there's a difference between I and I prime, and that's got to do with the information about tangent vectors that you're retaining to V. So V is just a set, but if you want to do geometry on that set, you want to know, well, what do tangent vectors to points on V look like, and what do things, two jets, like second order tangent vectors to V look like, and what do little infinitesimal surfaces on V look like, and all that kind of further information beyond just the set of points algebraically corresponds to knowing the difference between x and x cubed. That's not meant to be clear, that's kind of a subtle point, but we do want to distinguish between these two ideals. They have sort of different information about that kind of extra infinitesimal data, and the Grobner bases and all these algebraic methods are distinguishing them. So yeah, it's geometrically you have to go a bit beyond just the set of points to understand what the meaning of that distinction is. But yeah,
I love how you use two jets to explain this.
I use two what?
Two jets.
Two jets. Yeah.
Okay.
Wow.
So wait. So Dan, what happened to your usual beautiful handwriting?
I was writing with my mouse.
Oh wow, that's actually
Yeah.
impressive. Wow. You're still able to write super well with a mouse. That's
Albeit a bit
impressive.
slowly. Yeah.
Yeah. Cool.
Bigger.
Bigger. Yeah.
Other questions?
Yeah, any comments on the cheeseburger algorithm?
It was so hard.
Yeah,
Trying to give that little speech while you guys were talking about my pronunciation.
yeah, no, Buchberger you did pretty good.
I'm glad.
And then Billy made a joke about a cheeseburger algorithm being that you cheese the.
Oh,
I guess you cheese the tusk, right?
I see. I didn't get that at all. Okay, I needed the
Yeah,
explainer.
because the point is that burger, for some reason, is a banned word, but burger isn't.
Right. Yes. Okay. I
Oh.
get it. Okay. Yeah, if there's no further questions, I guess we'll call an official end to the lecture there. Thanks, Ken.
Cheers.
Thanks, Ken.
Yeah, so we have only 2 left. So next week
Yeah.
will be Buchberger, and then after that we'll have the actual elimination theorem, where we'll put all this to good use and get back to the geometry also, I hope. Right, so thanks everyone. We'll continue on with the exercise session.
All right. Good luck, guys.
See you all.
Cheers. Thanks for coming, guys.